Thank you very much for inviting me to speak at your conferences, and I've already been made to feel very welcome. I appreciate all your efforts, and I appreciate the fact that you're allowing me to speak in English, because otherwise this talk would be extremely brief. However, if I use complex language or you can't hear, or there are any points that require clarification, can you please indicate? I'm very happy to take questions as we go along. That's fine. It's much better to ask than just think, what the hell is he going on about? So this talk this afternoon, although I'm going to talk about a fairly specific example, I'm going to try and indicate that the ramifications or the significance is quite substantial, and that it's something that we as a community of researchers and scientists should be very concerned about. My initial title is quite pompous. It's Reducing Researcher Bias in Computational Science. And a more catchy title would be now I can speak and change slides simultaneously. It's a great example of concurrency. Oh, no, I can't. Right, it's okay. The more catchy title is It Doesn't Matter What You Do, Only Who Does It, and I'll try and illustrate what I mean by this in due course. The other thing, just as a little bit of background, I'm the head of department at the Department of Information Systems and Computing at Brunel University. Brunel is in the west of London, and it's a sort of fairly engineering, technical kind of university. And the particular example that I want to illustrate this talk with is the idea of detecting bugs, software bugs. And because this is problematic and it's very important for practitioners, this has been motivating researchers for a long period of time. And what would be particularly nice is if we could anticipate, we could predict which are likely to be the fault-prone components of the software system, so that we could focus our testing effort accordingly. So if you don't know anything, the only real strategy you have is to allocate your testing resources equally across the system. But clearly we can improve on that strategy. We could focus, if we know that either some parts of the system are in a sense coarse, or maybe a kind of kernel type of architecture, or we know that they're fault prone for some reason, perhaps because of our past experience or for whatever reason, then that would be useful, that would be advantageous. We could focus extra testing resources. Moreover, if we can make these kind of predictions, particularly in critical and safety critical systems, we could then make decisions as to whether we're ready to deploy, say, a new build or whatever, or we should continue testing. So clearly there are some reasons why this is an interesting problem, and therefore it's attracted a lot of research. But as I say, the results of this analysis actually go way beyond this particular application. One of my proudest inventions is this device here. It's called the Machine Learnatron. It's taken me a long time to devise, and as you see, it's a very clever machine, and I'll explain how it works. There's a hopper at the top, and into the hopper we pour some numbers. Numbers are good. It could be any kind of data, but numbers are especially good. And out of the machine, it produces answers. Okay, so it's very clever. It's a really good machine. I'm very proud of it. And in a small way, it's a caricature of how I think some unthinking machine learning research progresses. Machine learning is inductive, so we take examples, we go from the particular, and we try and induce more general patterns, models, theories, or whatever. But there's a danger in that process. It's a very powerful technique, or really a family of techniques, but we can stop thinking about what we do. Nevertheless, I have my machine. Sure. The questions are kind of implicit in the numbers. Okay, so I have my question, which then points me towards some sets of numbers in preference to others. So, I mean, clearly this is an extreme caricature. So if my question, if my interest, I want to predict, let's say, defects, for example, then clearly I'm looking at software defect data sets. But your question is well-founded, and sometimes we're so interested in the data we forget that there are questions in the real world beyond that. Okay, so that's my genius machine, which I'm very proud of. Unfortunately, lots of other people have been inventing their versions of machine learnetrons, and we have a very large number of alternative approaches. And then this leads me to a difficulty. Is my machine learnetron better than anybody else's? And so a lot of this work is fairly light on deep, there's not deep theory, so generally one approaches this in an experimental manner. That's the usual approach. And we generate large numbers of experimental results, and one could characterize the results as being somewhat confusing. In other words, no one particular approach dominates. We can't say that, if I point at that, oh, I've got to point it, no. I can't say that that particular machine learnetron is better than that one in any general sense. So we don't find that particular approaches dominate. Again, I'm somewhat trivializing the comparison. Clearly, there's a lot of subtlety. There are issues. We generally deal with large free parameter spaces and things like that. So the niceties or the details of how you compare different machine learning algorithms are quite subtle, but it would be a fair comment to say that no one particular approach dominates, and our way of shedding light on this question is largely experimental. So going back to this particular, if you like, question or goal, which is it would be really nice to predict where the software defects are likely to occur, in other words, which are the fault-prone components of a software system. We, some colleagues and we did a review of the literature, and using fairly stringent inclusion criteria, we quickly identified more than 200 empirical or experimental studies. There were, in fact, many more, but we applied some rules, and we said they have to provide a reasonable amount of contextual information, and the way that the experiments were conducted had to satisfy certain conditions. As I've already indicated, no particular technique dominates, and therefore we thought it would be useful to try and conduct a meta-analysis from these studies. We extracted more than 600 results to try and explain the variability in these results. And the things that we focused on were the type of classifier, in other words, what kind of algorithm was used, which you would hope would be the, the experiment is designed to say which classifier approach or which kind of algorithm does best. You would hope that that would lead, that would explain a lot of the variability in results. That would be what one would expect. We also looked at the kinds of metrics or inputs that the algorithms used. We looked at the data sets they were used to validate these approaches, and then we looked at the research group, the people who actually conducted the research. And I'll unpack that in rather more detail in a few minutes. But that's what we're trying to do. So we're taking lots and lots of primary studies, individual experiments. We're pulling the results and using quantitative statistical techniques in order to try and say what's the big picture and what are the things, the underlying factors that explain the differences in the algorithms that we're using. Right? It happens we're looking at trying to predict software defects. It could have been any other problem domain. So I think the approach and the findings go beyond just looking at software defects. So the actual review was published by my colleague Tracy Hall, and that's the reference. It's been available in Transactions and Software Engineering for the last few months. And to be specific, they located 208 primary studies that fitted the bill, if you like, so that provided, that were high quality, that provided sufficient information that we could use them for a meta-analysis. But once we started digging a bit deeper, we had to filter down from 208 and finished up. We only used about 20% of the results because we decided to look at a subset of all classifiers. We just looked at binary classifiers, that is, classifiers that differentiated between software component was fault prone or not fault prone. So there are only two labels or two outcomes, if you like. So we're using a machine learning algorithm to try and predict whether an unseen, a new piece of software, whether it's likely to be fault prone or not. We also got a little bit more picky about how they actually conducted or designed their experiment, and in particular how the validation works, because the problem, essentially machine learners are inductive. That means you give them examples or specific instances and then they try and find a more general pattern. So in order to see if it works, you need to kind of simulate the process of dealing with unseen data. If you provide the example, you train it on example and then give it that example back again, it would be a pretty useless machine learner if it can't give you the answer, because it just regurgitates, it gives back what it's already seen. So you need to simulate in some way or other the process of dealing with new or unseen cases. And this is usually done by a kind of cross-validation procedure. I won't go into a lot of details, but there are better and worse ways of doing this. And we sort of said there is a minimum standard. It's got to be reasonably rigorous in order for the data to go into our meta-analysis. Problem with meta-analysis, if you put junk into it, you may not get very reliable answers. Meta-analysis can't turn poor primary studies or poor inputs in, it's not magic. You can't turn poor things into good things. So it's one of the reasons that we needed to have quite strict criteria, quality criteria as to what studies we can use. In order to make some sense and to make sure we're comparing like with like, we need some contextual information. It's a great danger when you do machine learning research that you can forget that actually you are dealing with some real world phenomena. It's not just a data set that your mate kind of forwarded on to you. And there is a problem sometimes we get very distant from the phenomena that we're interested in. So we required some contextual information. And the final thing, which I'm going to unpack a little bit more, is we required either the confusion matrix or sufficient information that we could reconstruct the confusion matrix. So confusion matrix, and you need to this may seem unbearably tedious, but it's turns out to be moderately important. So I am going to go through this in a little bit more detail. So the confusion matrix, if you're looking at classifiers and you want to judge how good is my classifier, how well is it actually classifying, in this case, modules, and effectively, for a binary classifier, we've got 4 outcomes. So we've got, if you think of positives we could define either way, but it's conventional. We say positives are things that we're interested in. So in this case, a positive case is a software component that's fault prone. So you can we could divide, if we had an oracle or we knew the answer, we could divide all the software components into, say, this heap over here are fault prone, this heap over here are not. So we can make that distinction. So we would say the heap over here, the fault prone, are positives, the heap over here are negatives. And then in terms of the performance of my classifier, if I correctly say that a module is fault prone, then that's a true positive. If I say it's fault prone and it's not, then if I say it's fault prone and it's not, then it's a false positive. If I say it's not fault prone and it is, then that's a false negative. And if I say it's not fault prone, it's got the wrong way around. If it's fault prone, I say it's fault prone. I'm sorry, it's not fault prone, and I'm muddling myself up now. If I say this software component is not fault prone, and I'm correct, then that's a true negative. If I say it's not fault prone and it is, then it's a false negative. Okay. Yeah, sure. Okay. These things are I should know better, and I'm mildly embarrassed, but these things are a little confusing. So right, let's deal with the diagonals. These are simple cases, right? So if I say it's fault prone and I'm right, then it's a true positive. If say it's not fault prone and it isn't, then it's a true negative. So that's the ideal. So if my classifier, my prediction system, if you like, is working well, then we'll have very high counts in this diagonal. That's where we want to be. If I'm making mistakes, I'm going to be on the opposite diagonal. So if I say it's fault prone and it's not, then it would be a false positive. And if I say it's not fault prone and it is, then it's a false negative. No, I'm still got that the other way around. Sorry. So if it's not, all right. If I say it's fault prone and it isn't, it's a false negative, and if it's fault prone and it isn't, then it's a false positive. So those are the four conditions, and then what do we do with that confusion matrix is actually there are different ways we can measure from that and actually say how well we can derive different statistics to say how well is our classifier performing. Now, the thing that makes this a little bit more complicated than it might seem, and it's already seeming quite complicated because of my bad explanation, is suppose we have imbalance. Suppose that we don't get roughly equal numbers of false and negative cases, but let's suppose one predominates. And typically for software defect data, most components are not fault prone. Otherwise, we'd all be going out of business. There would, nothing would work, and people would be saying, "Let's junk all this computer stuff." So generally, fault prone or positive cases are very rare. Maybe, in a lot of the data sets that we analyze, you might be talking 1 in 20. So less than 5% of the cases are going to be positives, whether they're true positives or false positives. So the problem is, if you could think, well, the obvious thing, if I want to know how well my classifier is doing, you'd think I want to use accuracy, seems right. So you would say what proportion of true positives, what proportion of true negatives, because the higher I get, the better it is. But I could use a really naive or stupid strategy and get incredibly high accuracy. So let's suppose that 95% of the components or the cases are negative. Then a dumb strategy, I just say everything is not fault prone, I'm straight away going to be 95% accurate. But you wouldn't think that was a very good classifier, would you? It wouldn't be any use to anybody because you just said everything was okay because that's the dominant or the modal class. So you don't really want to use accuracy as a measure of performance because that's a problem. And therefore there's kind of quite a lot of issues, but typically people use something called the F measure, which is based on two other measures, the precision and the recall. We prefer to use a different accuracy statistic because it has some nicer properties, and it's known as the Matthews correlation coefficient. So that was the formula, but it doesn't really matter. And it's more stable. It deals with situations of very imbalanced data sets because it uses all four cells. So we deal, as I say, with where we have positive cases being relatively rare. It's easy to interpret because it's like any correlation coefficient that ranges from -1 to +1. So +1 means we've got a perfect predictor or classifier. 0 means it's random, there's no relationship. And -1 means that we have a perfectly perverse classifier. So if you've got a -1 correlation, you fix it very easily because you just put not in front of your classifier. Whatever it says, do the opposite. So at least, we have a statistic that has nice properties, and it's easy to know what it means. We can compare easily between studies, and we can, if we want, we can do some inferential statistics because it's closely related to the chi-squared distribution. So we just take the square of the correlation coefficient multiplied by the number of cases that we're dealing with. So we can compute the chi-square value if we want, and therefore test for significance. In our meta-analysis, it was reasonably well distributed. So this is the QQ plot, the quantile plot. And although there's some slight deviations at the two tails, so we've got this indicates we've got a slightly peaky distribution. It's fairly reasonable. So that's a useful feature as well. I mentioned that it's quite popular, a different approach that many prior studies use, which is known as the F measure. But we see particularly with poorer performing classifiers. So there's a convergence as we get towards perfect classifiers. But the worse the classifier, and particularly where we're dealing with random, so this is a 0 correlation coefficient here, but you see a 0 or a random classifier, one that's simply guessing, generates quite a range of F value measures. So you can see that the F value measure could be quite misleading, and this is a problem. From our meta-analysis, this is the distribution, and as you see, as I mentioned earlier, it's reasonably symmetric, and although there's slightly stretched out tails and a little bit of a too much peak, lack of shoulder, it's not a bad distribution. But the interesting thing here is some of the values, and these are all values that have been taken from refereed, published, high-quality studies that presumably the community is quite chuffed with. So this is the significant point. This is, at this point, we're dealing with random results. So anything to this side of 0, in other words, any negative correlation, is actually doing worse than guessing. You've done all this, or these researchers have done all this clever machine learning research, applied all sorts of sophisticated algorithms, and the upshot is they've got a classifier that's worse than if you just guessed. Or, we have, I don't know, in the UK, traditionally people did all sorts of weird things when they wanted to know the future. They looked at tea leaves and things from a cup, and you turn upside down and look at the shape of the tea leaves. That would be a better strategy in some of our machine learning algorithms for trying to classify. And that's what's disturbing, is that it's not necessarily clear to people, either the people doing this research or the people who are reviewing it, because it doesn't seem to have elicited much comment. So to summarize, we've got about over 4% of results are negative correlation coefficients. These are people who could instantly improve their performance by just saying, whatever my classifier says, do the opposite. And we have a quarter that have a correlation coefficient of less than 0.1, which is very, in terms of effect size, that's very, very close to 0. That's such a small effect, it's really not worth getting excited about. So to all intents and purposes, a quarter of our results are not would be hard to differentiate practically, even if we can show statistical significance. Practically, you couldn't differentiate between that and just random. To cheer us up, we have a few that are quite good. We have 3% are better than 0.7, which would be seen as a very large effect size. Actually, the lowest correlation coefficient in a published journal was minus 0.5, and there's tables probably a bit small to read, so it's not really, don't worry about that. But you know, they published all the figures, and then they concluded, despite our encouraging findings, external validity has not been fully proved yet, and further empirical studies are needed, especially with real data from industry. I mean, and this was in a high quality, it's easy to point finger at people, so I won't name the authors, but this is in a high quality journal that I think the computer science research community would say was a good journal that is rigorously refereed. Yet, because if we don't think carefully about how we measure performance of our different algorithms and our research, we can completely mislead ourselves. And this is an example of how researchers completely misled themselves. Yeah. I'll need to go and check. I think they are working in the US, but I don't think that was their home country. But I could check that for you. Why do you ask? I'm going to skip on. Actually, I presented some of this at a previous event, and people were taking fragments of text and already dropping them into Google Scholar, so I'm moving on before you can do that. And partly, I want to give the example of how I think we collectively mislead ourselves, but it is a little bit mean just to single out one group or another, because I'm well aware that people could look at past papers that I've written and say there's that mistake, and the other, and it's not about particular individuals. It's saying it illustrates that I think we need to be very aware of how we evaluate the performance if we're doing algorithmic kind of research, this kind of computational research. We need to be very meticulous as to how we actually judge it. And none of the things I'm saying here are particularly deep, but we seem not to collectively thought about it too much. And that's a shame, because 200 plus primary studies is a lot of effort. That's many person years, that's many tens of millions of euro have gone into research grants. And much of the work is practically unusable, because either way people report the data or just how they do the analysis. Anyway, to move on a little, so I'm using this correlation coefficient as the response variable in order to be able to compare like with like, because there are lots of different performance statistics people have used. We've reverse engineered wherever possible a single performance statistic, which is this correlation coefficient. So the next thing then is to see how the different types of machine learning algorithm perform. So we've got, from left to right, we've got artificial neural nets, naive Bayes techniques, benchmarks are just comparing with some dumb normally using the modal class, case-based reasoners, various decision tree approaches, which include random forest, regression-based methods, search-based, which would be anything from greedy search to sort of population search, like genetic algorithms and things, and support vector machines. And what you can see, which is just confirming my early point, which is no technique dominates, is there's a huge amount of overlap. And if the horizontal bars indicate the median value, and then you can roughly interpret the box as sort of being kind of confidence limits, if you like. It's not strictly so, but it's giving you an idea of the variability. Then there's a range of input type. I'd probably skip over it. You can imagine different classifiers look at different input types. And again, we find a lot of overlap from that. We also looked at whether we could, the different data sets, whether the sort of variability associated with that. And again, whilst there's a wide variety of data sets, there's sufficient overlaps. There's two data sets that are particularly used. There's the NASA one and the Eclipse defect data sets. So we can actually get a lot of comparability across studies. And again, we find they don't have much explanatory value. And finally, I don't know how well you see this, we thought it would be interesting to look at who does the work. And we defined research group as co-authorship. So the nodes here represent people, and the edges are links whenever somebody co-authors with somebody else. Initially, I thought it would be interesting to look at institution, but that's kind of unworkable because people move. Institutions are generally quite large, so people could be in different buildings and actually never talk to each other or have anything to do with each other. So it seemed much simpler to use a clustering algorithm that simply links whenever anyone co-authors. Just having, you can see this generated 23 different distinct research clusters. Some of them are quite large, like that cluster there. So in that cluster we have 10 people are connected. It doesn't mean 10 wrote all the same paper, but by a chain of co-authorships they are linked together. And at the other extreme we've got, somewhere is a singleton, if I can see it. Oh yes, this cluster here. So this is like Professor no mates. Okay, so this a very solitary person who doesn't work with anyone else, probably has no friends, and it's quite tragic. But anyhow, so this is how we defined research group. From this, to actually conduct the meta-analysis, we used a very straightforward procedure. We used a four-way linear ANOVA model. And the thing I really need to stress, well, two things I want to stress is, one is we used a random effects approach, which what that means is I'm not interested in trying to use the meta-analysis to say that, let's say, support vector machines are lead to significantly higher or more accurate results than, let's say, artificial neural networks. I'm just saying of the different factors, which factor explains more of the variability in the results than other factors. Okay? So I'm not trying to say which technique does best, I'm just trying to say where does the variance come from. And that's sort of subtle, but it's quite important. What it also means is that if there are different levels for a factor that we haven't yet seen, then in as much as we're sampling randomly, then we continue to explain unseen levels. So it gives a little bit more generality than if we simply compare particular values, if you like, or levels of each factor. It also gives some advantages in terms of it saves me having to do very large numbers of significance testing, and then I'm going to get myself into problems because I run out of I don't have enough observations to deal with the adjustments I have to make to the significance threshold of the alpha. Anyway, there's some kind of statistics here, and what we're trying to say is which factor matters most. And from the results, let's pull out the important stuff. So the first thing, research group, author groups, I've changed the labeling there, which is foolish of me. We can explain in quotes, all right? Okay, we can be kind of precise and say explained is probably not, I haven't shown causality, but we can associate nearly a third of variability in the results with who does the work, okay? And that factor dominates. At the other end, the thing that you would expect, because the experiments are designed to find out which type of classifier, which algorithm, which technique does best, explains slightly over 1% of the variability in the results. So ballpark, who does the work explains 25 times more of the variability in the results than what they do. And that's not a good place to be at. And I suggest that that is something that we as a community need to deal with, or those people care about these things. And again, if the percentages want some unpacking, just it's a little bit shorthand. In terms of what you might think of as effect size, we might consider something of the order of 14% to be a large effect, and something of 1% would be a small effect. So we're saying that what choice of algorithm you use, whether you use the support vector machine, how you parameterize it, that is a small effect. It'll have, in the round, about 1% impact on the results. Who does the work has over 30%. And that's a very large effect. How can this be? I'll skip over compact. I'll come back if anyone wants to argue about it, but I'll skip over the kind of some of the confounders that we tested for. Seems to me that suggests we have a problem with researcher bias. Now, bias is a very value-laden word. It sounds, like evil people are making up their results, fudging their data, doing terrible things, and I'm not saying that. But nevertheless, something is going on such that if I do the work, it leads to a different result, maybe more accurate, less accurate, who knows, than if one of you guys did the work. And who does the work matters a huge amount. How can that be unless who does the work is biasing the results in some way? As I said. So what are the potential sources of bias? Well, the first one that we believe is important is expertise. Many of these algorithms, even some statistics, you think what could be simpler than like just building some regression model. But the kinds of transformations that you might apply and actually how you manage it are quite subtle. So somebody who has a good statistical training might build much better regression models, or much more stable regression models than, if you just, I don't know, go and get some standard statistics package, take all the standard, settings and just say, I want to do a stepwise multiple regression procedure, and click the button and it comes out with the equation. The two aren't the same. So there are expertise issues, even with things that don't look like they're terribly complicated. Some of the more sophisticated techniques are, very subtle, and if a team has had many years of expertise, they might use the technique more effectively than somebody who's just using some online tool set like Weka or something and just taking the off-the-shelf defaults. The second area I think is causing difficulties is that we don't have agreed reporting protocols. There's lots of pre-processing of data that needs to be undertaken. There are all kinds of things that would happen, all sorts, we generally have very large free parameter spaces, and lots of that's simply not reported. So it's not easy, even if you had the expertise, that you can necessarily reproduce the results. My team might come up with some results. We publish in a fairly informal way. Lots of information you need to know is not visible. You think, we can get hold of the data, we know the algorithms, we should be able to reproduce that. And probably you can't, because there's lots of things you need to know. The third area is, I think, and it's undeniably true, is that we have preferences for some results over others. On my laptop here, sitting on the well, it's not even a hard disk anymore, it's solid state, but stored on my laptop are lots of half-completed studies, data sets, papers I've started to write up that I haven't finished. And like many of you, I have many demands on my time. I regret that probably some of the data and some of the half-completed studies will never be written up and published. So how do I choose which ones I'm going to work with? all kinds of ways. But one of the things that drives me is I will be, even if it's not conscious, I'm informally thinking, that's a more interesting result than that one. Well, that's easier. That's a really simple, it's a really sweet result. It confirms the results of, 500 groups around the world. That's good. That will be, I'm sure that will be accepted at the prestigious conference or wherever. So it gets written up. Something else which is mushy, controversial, hard to make sense. It's not that I'm saying I'm hiding it from anyone. It's just I never get round to writing it up. And if I never write it up, how will anyone else know about it? So we have these kinds of bias going on. And because that one is so common, it's not unique. It's not computational scientists that are worse than anyone else or more wicked than anyone else. It's a common process. In psych, it's actually the name for this phenomenon is known as far draw problem. And this was identified or given a name some years ago by a different community, by some psychologists. And it's certainly something that exercises clinicians, because when they try and do meta-analysis of many studies, that they might have a particular medical intervention, some new drug, some surgical procedure, whatever, and you want to know, does it work? And you need to get all the high-quality studies, all the high-quality primary studies together and analyze it. And the problem with a lot of meta-analysis is going to be misled if the only studies that are in the public domain are ones that are positive or confirmatory, because ones that were neutral or hard to understand never got published. So far draw problem is a source of bias, and it goes way, way, way beyond computational science. It's a widespread problem. But it may also be an issue as to why, when we try and do meta-analysis and say what explains the variability in results, we're finding things like the research group is more important than what they actually do. So how can we deal with these problems? I think expertise, one of the things we can, and we have very large, as I say, parameter spaces. One of the things we can do is and we're actually starting to embark on this, is actually larger studies involve different groups. It's well known that some groups are good at particular techniques. So why don't we do studies where the case-based reasoning is done by the group at the University of X, but the regression modeling is done by statisticians at the University of Y? Because the danger otherwise is if one group does the lot, they're probably very good at their pet technique. So if it were my team, myself, we'd probably make a half-decent job of the case-based reasoning, but lots of other things we don't know about or we don't care about. So we're comparing doing case-based reasoning very well with, support vector machines in a kind of unthinking, naive way. Well, us finding that doing something well does better than doing something else badly isn't really a useful result, and it actually is unhelpful in terms of the community making sense of where we're at. So I think studies that go across groups are something to consider. I think reporting protocols are extremely important. It's well known we have, the sensitivity of results to unreported details is well known, well understood, and that's something the community, the journal editors, the conference program chairs and people have to take into account. And the final thing, in a sense, how do we deal with our preference for some results over others, is that we need to do blind analysis. And that's something that I've now undertaken, that experimental work that I and my team will do from now on will use blind analysis. And by that, I mean you need at least two people, and somebody takes the results and takes the label of the treatments away. So let's suppose one treatment, if you like, is case-based reasoning, another is, I don't know, something, just some kind of benchmark technique. We throw away those labels and we do the analysis not knowing what the different treatments are. So the fact that I might have a built-in bias, even if it's subconscious, to doing case-based reasoning is at least reduced by the fact that I no longer know which of the results that were due to case-based reasoning. So, just to wrap up, because I'm running out of time. I don't think we can ignore the fact that the main determinant of a validation result is who does it. That's something that we can't just sort of forget about. And I don't think computational science can be seen as such until we find ways of generating routinely verifiable knowledge. And it seems we're far from that. Thank you.